And thanks the organizers for the opportunity to present my work here. Okay. Today I'm going to present you a work about a renormalization method to tackle nonlinear dynamics, or the nonlinear dynamics of quantum many-body systems in general. Okay. So the dynamics of quantum many-body systems, it's a very challenging problem, mainly because the exponential growth of Hilbert space with the number of particles. Probably all of you more or less know about this, okay? And this represents a reachable memory requirement for a large number of particles, okay? So roughly speaking here, if you want to calculate expectation value, the dynamics of an expectation value, you have to calculate the dynamics of two-body correlations, which in turn depends on three-body correlation and so on, okay? And in the end, you have a linear hierarchy of differential equations for the correlations of the system. So this is a very challenging problem. And what people typically do is to use truncation approach, okay? So a very used approximation is this, for instance, a mean field-like approximation. Here I can call a semi-classical approximation because the self-correlations are kept, okay? And this is very often used, as for instance, Celso said here, for the EIT problem with long-range interactions and a lot of other types of problems, okay? And we can go beyond this up to two-body correlations, neglecting three-body correlation, more precisely connected correlations, okay? But in all these cases, if you go beyond this, indeed, we get truncation. We get nonlinearity in our equations. Okay, so we have to deal with nonlinear differential equations, and linear algebra approaches are not useful anymore. This notion of a many-body spectrum is a bit lost. Okay, the idea here is to tackle this kind of problem with an old renormalization method. And try to extract some information, okay? That's the idea. So, okay. I am working now in this kind of approximation here, but to demonstrate the method, I just use this first one, okay, just to demonstrate the feasibility of the method and the implications. So let me consider a generalized semi-classical dynamics where we have here generalized interaction. So it can be short and long range, okay? So the long range it's included here. And here we have a matrix which is diagonalizable, but it can be norm-Hermitian, okay, in general. And here we have a vector, a complex vector that represents a non-homogeneity, okay? So this is a kind of system of differential equations where we are using Einstein rule summation, okay? And what people usually do is to write a code, using the Runge-Kutta method, okay? And for one realization of this kind of system, you cannot parallelize, for instance. So if you want to obtain a large number of particles, with a large number of particles, if you want to obtain results, you cannot parallelize. That's the idea. So this is very hard, okay? And if you use an analytical solution, even approximated analytical solution, you can, for instance, parallelize and get faster results, even in this kind of approximation, the semi-classical case, okay? So what we do here is simply transform this kind of differential equation into an integral one, okay, where g is the green function, but here in the matrix notation, okay, and where this g function here is satisfy this kind of equation here for independent particles, and here in this line is the first line of this integral equation. We have the free term where their particles are independent. And then we can use the iterative process by substituting this free solution here that we can analytically solve, okay, into the interaction term. That's the idea. This is common, okay? And we can find a formal expression for this propagator, for this G function, in terms of the eigenvectors psi and eigenvalues of this matrix here, which we assume that we can solve, okay, analytically. That's the idea. So using this form of this green function, if you precisely define your matrix, you can solve analytically the eigenvectors and eigenvalues, and then you will obtain an analytical solution in naive perturbation theory, nothing more than that. What we could call naive perturbation theory. So what happens similarly as in quantum field theory, we have unphysical terms appearing here, okay? So here, for instance, we have a typical coefficient depending on the interactions. If we stop at first order, we have first order corrections here in this coefficient. And of course, this coefficient depends on the eigenvectors also, right? But we have an integral here between products of exponentials, okay, over this product. When this kind of argument here is 0, when these frequencies are equal, we get unbounded evolution here, and we have no cooperative shifts and decay, cooperative decay and shifts in these eigenvectors and in these eigenvalues. Sorry, okay. This is expected when you have quantum many-body system because the quantum equations are linear, okay. But when we use only naive perturbation theory, there is no many-body corrections and in this solution here for naive perturbation theory. The idea is to use a trick, old trick, applying these kinds of modern many-body problems, okay, where we add here an unknown frequency. We add 0 minus a frequency here plus the same frequency, and we redefine a new eigenspectrum here. So we are renormalizing this frequency, or this, for open system, we have decay also, okay? It can be a dissipative problem. And we expand only this part here in series expansion, okay? What we get is this kind of expression here, where we have the exponential of the renormalized eigenvalue, all right? And we have the expansion here. So in this coefficient, if you select precisely this unknown frequency in order to eliminate these unphysical terms, sometimes named secular terms, what we obtain is a many-body correction to these eigenvalues, even for nonlinear equations. Okay, so we can estimate these eigenvalues, which are important for the dynamics in general of quantum many-body systems. Okay, so let me present an example here. The idea is not to be very rigorous in physics, but to demonstrate the implications of the method. Okay, in a kind of example, I am using here an atomic cloud emitting light cooperatively. So cooperative spontaneous emission from n2 level atoms. Okay. Okay, R is the standard deviation of the Gaussian distribution of this cloud. We can, for instance, prepare this atomic cloud with an incident laser and switch off fast this laser and see the power decay in time. In the semi-classical approximation in the far field, we can obtain this power decay here in terms of only expectation values. So here we have an approximation, the mean field approximation, but in the case of equal index, we separate the single atom case. Okay, so we have here superposition. It's not completely classical. Okay, so in order to obtain this power here, okay, this power, we have to solve this differential equation where we have here the long-range interaction between the particles or between the atoms. So if you want to calculate this expectation value, you have to calculate the expectation value of all particles, okay, of all atoms. And here we have the single atom physics. And then we can define our matrix that I previously presented to you. So all terms here are diagonal, and you can easily solve the problem, okay? So the long-range expression here, it's the light-mediated long-range interaction that comes from an integration over the vacuum modes of the electromagnetic field as presented previously by Hoban-Kaiser, okay? And we can use a mean field-like initial state where PE as an initial condition, okay? Where PE is the probability of excitation of all atoms, considering all atoms in the same, with the same probability of excitation. And we have here in the coherence of these states here, a phase profile which can generate the superradiance and subradiance, as you probably have heard here, okay? In the limits of low excitation in the linear optics regime, we can obtain the coupled dipole model as presented before, okay? And the total power, the total classical power here is simply the product between the two operators. So with these two models with long-range interaction, we can compare both cases and see if the renormalized solutions can separate some non-classical effect or the semi-classical effect from the classical effect, or the semi-classical superradiance or decay or subradiance, okay? Subradiance. So in this plot here, I compare, in the classical case here, exact diagonalization with the renormalization procedure. Of course, to do this kind of comparison, we have to consider the low excitation regime in your analytical solution, and then we can compare and see what happens with this kind of effective spectrum or these effective eigenvalues we obtain with the renormalized solution. So we plot here this histogram, okay, and in 5 minutes, 2 minutes, okay, 3 minutes, okay. So I have 2 more slides only. Okay, in this, so in the vertical axis we have the decay rates, and here we have the cooperative shifts with exact diagonalization. If you calculate the average decay rate, we obtain here in the exact diagonalization the single atom decay, okay? But here, in the renormalized solution, we get something different, mainly because our eigenspectrum, or effective eigenspectrum depend on initial conditions, which is a bit different, okay? And when you calculate the average here, we get a superradiant decay, okay? Which is here in the solid line. So just to demonstrate, this slide is just demonstrate that this new spectrum is different and depend on initial conditions. So you have to set this initial condition, and you have no generalized description. So this is a pay you have to pay, a price you have to pay, okay? But interesting is that we obtain a linear scaling with the cooperative parameter that Hoban just presented, okay? So this is a good prediction of our theory in the low excitation regime, okay? So the last slide now. In the nonlinear case, what we have is a correction. It's a nonlinear correction of this linear optical thickness, okay? So here we really compare the analytical results with the numerical results. So in the solid line, here, we obtain, we have the single atom decay of the power in time. This is the dimensionless time, okay? And here we can see a good agreement over several times with the renormalized solution, okay? Renormalized solution in the semi-classical case with the numerical case. And we can clearly see here a cooperative reduction in the sense that the classical case is farther from the single atom case than the semi-classical case. So the classical case predicts more cooperation than the nonlinear case, okay? And here we have the superradiant phase, the superradiant stage, followed by superradiant stage. Okay, but the superradiant stage here is too small in this with this cooperative parameter. Then we can increase the cooperative parameter and clearly see a good agreement in the superradiant phase, so a more accelerated decay here. Okay, of course, in a smaller range of validity. Okay, so that's the idea. So let me finish here, concluding. So we have presented a renormalized solution, which is valid for longer times than power series solution, okay, for stronger interaction than simply power series solution. An estimation of many body decay rates, okay, many body spectrum, and we are able to detect some difference between semi-classical and classical effects. In this case, a cooperative reduction considered a semi-classical case. Okay, of course, the more important goal, it's working now. It's work in considering quantum many body correlations. All right. So thanks for your attention.